So welcome. Good morning, everybody. Today we have the annual PhD presentation of Mirko Goldman. He's going to talk about online learning strategies for optical neural networks and photonic circuits. Please.
Thanks for the introduction. As I said, my talk is called Online Learning Strategies for Optical Neural Networks and Photonic Circuits. But I want to start with something slightly different, which is the current digital computing environment we have. And there, if we look at the physical substrates we use, we start with transistors that can be used as binary switches, and we do some digital information processing based on zeros and ones. We can cluster together these transistors into gates, which build logical units. We have some decoupling between memory and processing. That means we have the von Neumann architecture where we have the CPU that does actually the information processing, and we have the RAM where we store the information. To run some programs on these devices, we need to write code that processes logical structure. And finally, if we think about our daily use of these hardware, we just translate our intention into code. And then we actually don't need to think anymore about these transistors, which is a quite elaborate way to use these devices, because here we don't need to think about physics anymore. It's just about how to process information. If you now look what is going on in the last years, we see that there is a huge increase in the computational resources that are needed for running certain programs, for example, or especially AI programs. If you see here, the blue dots are different AI models, especially here there are large language models. And you see that in the recent years, there's an explosion of need in computational resources. So on the y-axis here, we have petaflops per second days. That's kind of a measure like light years. And if we then look at the hardware, we see that we also have an increase in the performance these devices can give. But also on the same side, we also see that the peak power, so the energy consumption of these devices increases just linearly, together with the energy consumption. Based on those two plots, I think there is right now a need for new computing hardware on the one side, but also new computing paradigms. And this can be on different scales. So on one side, we could design general purpose information processors. That means you build hardware that just based on any information that is given can compute certain things you want. Then there are application-specific small-scale processors. This is, for example, in the telecommunication branch where you want to have like a signal recovery. You only have really a small processor that does a specific, or that is designed for a specific application. And finally, one could design plug-in accelerators for digital computers. That means you look what is slow or energy consuming in the digital domain, and you just replace it by faster and more efficient devices. And one of these new paradigms is called physical computing. And for physical computing, you need to solve two different tasks. On the one side, you have the design of physical computers. There you need to think about which architecture you want to use, for example, either the von Neumann bottleneck, or you go towards in-memory computing, which is a bit more brain-like. You have to think about the substrate you want to use. Right now, most of the things are in electronics. There's a huge effort in photonics, but there are also different things in chemistry or mechanics. Then the computational modality. If you want to be more energy efficient, it might make sense to go towards the analog domain. Again, the purpose is important. And finally, you have to define some performance metrics. That means, do you want to design a computer that is energy efficient? Do you want to design a computer that is fast or leads to a high precision? And on the other side, if you have designed a physical computer, it's important to also program that computer. And in the programming path, I separated it in 3 layers. So at the intention level, you need to define a computational objective. It could be classify images, predict time series. Based on this, you write an algorithm. This means that's a finite set of rules that guides towards solving the computational objective. And then in the lowest layer, you have some interaction with the actual physical computer. That can be anything from a spiking electronic chip to laser, for example, or a photonic integrated circuit, which I'll show later. And then you have somehow a loop. You feed your inputs to your physical computer. You measure with sensors the processing that goes on in the physical computer. And then you have this update loop here between the metrics, the optimizer, and the physical computer that try to optimize the processes in the physical computer to solve your task. And based on these two sites, in the following slides, I will talk about, given an analog photonic substrate, how can we program it to exploit its computational capabilities while learning to solve a task from data. So how can such photonic substrates look? I worked in the last year with two people from the post-digital network. That's on the one side, Anna Scali from the UBFC in Besançon. And they have implemented a large area VCSEL that they use as a neural network. In this setup, you have a DMD, which is a digital mirror device. You have their mirrors that can be flipped. So you have binary encoding of information. And what we did here, we encoded these MNIST images, that's digits from 0 to 9. We encoded them on the DMD. And then the DMD is illuminated by a laser. This projects the data into the intensity of the light. And then it goes through this input weights encoding path, where we have an SLM that for the first part is set random. So you have a random phase modulation here. Then you go into a multimode fiber, which just scrambles up the entire signal. And finally, you project this signal onto the surface of the large area VCSEL, which is a laser with a spatial expansion of 70 microns. And this performs a nonlinear transformation of your input signal. And finally, what you do here is you read out the response of your laser. And you can then weight this response with different devices. You can, on one side, either use a DMD, so you have, again, a binary weighting of your signal, or you use an SLM now in the intensity modulation, and then you have like up to 10 bits resolution in the output weights. And the final thing, what you do is you collect the entire signal weighted on a single photodiode, and there you really get your output of the of your task. So you only measure a single signal while the entire processing is in the VCSEL encode. Finally, to the current state of the setup is that there is not really a physical model of this device. So going towards those sizes of 70 microns, it's really hard to model the dynamics in the system. And accordingly, we don't really know what is going on in the VCSEL when we project the MNIST images. And towards the tunable parameters, in this input SLM, we have we can illuminate an area of 200 times 200 pixels. That leads us to 40,000 weights, which is quite already a huge scale. And in the output, we used a DMD in the beginning, and there you can really flip mirrors on kilohertz rates, and you can see that some training algorithms there run or converge within a minute, which I'm going to show later. The other setup was designed by Tigers Yunusi from VLC Photonics. He designed a photonic integrated circuit, which can be used for adaptable convolution. What you want to do with convolution, you have a temporal signal where you have information encoded sequentially. And the idea is that you sum up the sequentially encoded information to get a targeted signal. The chip that was designed by Tigers has 16 channels here that all have a different length and therefore encode a delay shift. And after they all get these different delays in the 16 channels, they get summed up And the goal is here to optimize the signal that is summed up. And again, here we have for every channel a Sender modulator with which we can modulate the signals of the individual channels. But there's not really like a model because there's strong crosstalk between the different channels, and it's hard to just we don't have much knowledge of what is going on in the chip here. So now, having shown these different hardwares, the programming strategies or the learning strategies that were used here are the two ones I show here, which is the extreme learning machine or the reservoir computing concept. What we do here, we exploit the inherent information processing of physical systems by using a random data injection and also a random data transformation within the physical system. And you can see here for the extreme learning machine, you want to do classification or regression based on static data. That means that's images or time-independent measurements. And for the reservoir computing scheme, you want to do time series prediction or continuation of temporally dependent signals. For both, we have kind of the same scheme. We have our input data here and here. This input data is projected into the physical system by some input weights that are set randomly. You get a response out of your system, which is here the a feed-forward network, and here it's modeled by a recurrent neural network. And then you have your output weights that read out what the system processed, and based on this, you can the W outs here are the only optimized parameters. With this, you can get out what you want from the system. And to optimize these setups, you have two parts you can optimize. I said you optimize the output weights here, but you also have some coarse-grained parameters like the input scaling of the input weights, or in the recurrent neural networks, you have, for example, the spectral radius, which gives you like how strong the signal is reverberating in the recurrent network. So now let's look at the computational capabilities of this reservoir computing paradigm. And what we do here, we use the MNIST task again. We have the digits from 0 to 9. We project them into a random network, and we only train the output weights to classify which digit is actually shown. And what I show you on the right is the performance, so the accuracy of the classification compared to different sizes of the network that I used to classify the digits. And you see for the reservoir computing concept that increasing the size of the network improves the performance. So without training the internal weights for the network itself, only training the output weights, you can see we achieve accuracy above 95. However, the question is this randomness in the hardware actually guaranteeing efficient use of the hardware? And if we here look to current success in digital deep learning, for example, we see that performance in these deep learning systems actually come with the scale of the trainable parameters, which most of the times scale quadratically in the number of neurons you have. They also increase with training time and with the amount of data. So this is some plots for large language models where you see that the training loss goes down with the amount of compute you put, so the training time, the data set size, and also the number of parameters the model has. Based on this, we here stepped a step forward, and we used just for simulation purpose backpropagation of a digital simulated model, and we trained the system now by optimizing these input weights as well. And on the right side, you now see that for the same system size, we increased the performance quite a lot. That means training these input weights, we optimize the efficient use of our network, and we need much less neurons to get the same performance compared to the reservoir computing paradigm. And yeah, the scaling here is that we get the same performance for 10 to 20 times less neurons. And if you want to build efficient hardware, that's actually a scaling factor that matters. The problem, however, is, I said here we use backpropagation. If you want to train this input weights in a physical system or for a physical computer, it's not clear how to train these input weights. So there is still a challenge how to optimize these input weights. So the goal would be to find an algorithm that, given a certain metric, like the error that you measure between what the system has as an output and what you want to have as a target, optimizes the internal and hidden parameters efficiently. That means, for example, we want to get like delta W in that we can use to update our input weights step by step to go towards a lower error at the output. And therefore, I came up with a couple of criteria that I show you here on the right. So first of all, we want to have a learning strategy that is scalable. That means, as I said before, for reservoir computing, you have these coarse-grained, small-scale parameters. But here we now want to shift towards large-scale optimization, so you have a huge amount of parameters, and these parameters are more fine-grained. That means they have some more local character. The second point or second criteria here is that we do not want to have, or usually we don't have, much system knowledge, and therefore the learning strategy also should work with almost no knowledge of the model of the physical system. The third point is, if we want to build physical computers, we don't want to use so much digital computers on the side. That means for learning strategies, it would be nice to have only a minimal amount of digital computation, and therefore we would move towards autonomous physical computers. Then we have as a next point the convergence speed and sampling efficiency. That means how long does it take to converge to a minima, and also how much forward passes we need for our optimization. And finally, that's a point that's not so important for digital computing, but now for physical computing is quite important. We need some robustness. And that means robustness against device mismatch. That means if we want to design a learning strategy that trains a physical computer, we produce these physical computers, and they might all differ slightly from each other because of imperfections during the production. And we want that our learning strategies actually can train independent substrates. We want that the algorithm is robust against noise, and also something that in digital computing is not there. We want that our algorithm works with quantization of parameters. That means we have some limited resolution of the input weights, for example. They only have 10 bit. They are not full resolution. They are not floats, for example. And finally, the last point is that given such a learning strategy, there are a couple of them that need some requirements on the physics of the substrate. That means the physics need to fulfill some boundary conditions which limit the amount of physical computers we actually can apply them to. And therefore, this is the last point here. We want minimal boundary conditions on the substrate physics. Finally, also, if we think about different substrates, as I said, you can implement physical computers in electronics, photonics, chemistry. You want that the learning strategy should exploit the strength of your physical substrate. And I will show that this later can be done. In the last couple of years, there were some learning strategies published, and I will just show 4 of them, compare them later, and then decide what is nice for photonic substrates. So on the left here, we have the backpropagation through a digital twin. That algorithm works as follows. we have some input and parameters that we send to the physical system. The system does some processing, and we can measure at the output the difference between what we want and what we actually observe. Then we go towards the digital domain and compute the error between those, the target and the output, and use a model of our system to compute how we update the system. And that's a loop. So we do the forward pass in the physical computer and the backward pass where we get the update of the parameters we do in the digital domain. And you can see in the blue line here that if you do it in that way, that you do the forward pass in substrate and the backward pass digital, you can actually improve the performance of the image classification. If you only use the forward pass also in the digital and the backward pass in the digital, you see that the optimization does not work because there is a mismatch between the physical system and the model. As always, you have some imperfection in the production, as I said, and those deviations can lead to failure of the training. The second algorithm is called augmented direct feedback alignment. This is quite close to the backward propagation algorithm. You here compute an error, and you project back this error based on, for back propagation, based on the weights you know and the activation function you know. If you go towards direct feedback alignment, you replace actually the weights for the projection with some random weights, which are here B, L of T. So you don't fully know the weights of your system, but you replace them with random weights. And this was shown to actually work. So there's some alignment phase between the algorithm and the physical substrate. And then over time, this aligns. And recently, they also showed that you can replace this activation function by a function that is only linearly correlated to the real function. That means you don't really need to know the exact function of your neurons. You just use something that scales in the same way, and still this algorithm optimizes and was used to train for this endless classification, and you get a good approximation. Finally, there is a mechanism that is quite close to physics, but has some strong boundary conditions on the physical substrate. The algorithm is called equilibrium propagation. Here you use an energy-based model, and this model has or needs to have bidirectional symmetric weights within the network. You have here your energy function, and then you use two phases. In the first phase, your network evolves freely towards a fixed point, and yeah, it evolves based on the input you give. And then in the second phase, you slightly nudge the energy function. So E is here added with this nudging term towards the correct output. And due to the nudging, you see that your network slightly adapts. You get a new fixed point. And just by looking at the fixed point in the first phase and in the second phase, you can compute an update rule for your weights. And it was mathematically shown that this actually approximates back propagation. However, you need this energy model, and you need to know what is the energy function of your system, which is for many complex physical substrates, it's not given. And finally, this is a quite brute force search algorithm. You can do random search. So you do something like you try, check if the performance improved. If not, you go back. If it improves, you stay there and try to do like new adaptations. And if you do this step by step, you start with some initial parameter settings. You can go just by these brute force algorithms towards a local minima. If you now compare these shown algorithms, you see that all of them have some advantages and disadvantages. Here I generated this overview especially for photonic systems. And what you see is that, yeah, reservoir computing is quite a good candidate, but you see it's not efficient usage of the hardware, which I show in the first slides. You have the backpropagation with a digital twin, which has a huge computational overhead, which is offline because you need this digital model. We have the augmented direct feedback alignment, where you have the you need some knowledge about the system, and you also need some digital computer that computes your updates. And finally, the equilibrium propagation. You have these requirements on the system dynamics, and also you need this knowledge of the energy function of your system. The last algorithm which I showed was the simple search algorithm, which is quite autonomous. It doesn't need much digital computation on the side. However, to get towards the minima, you need a lot of brute force search. And this is, the computational overhead on the physical substrate is extremely high. Now, looking at this, I was wondering what is the perfect match for the photonic systems I presented in the beginning. And as I said, for both, they have quite high inference rates. That means we can pass through data really fast. We can show these images here with 15 kilohertz. And also for the photonic integrated circuits, we work on the level of 11 picoseconds per, the sequential encoding is at 11 picoseconds, so we can pass through a lot of data within short time. So can we actually exploit this fast inference ability with this learning algorithms? And then I think there is quite a nice match with the simple search algorithm, because they have the disadvantage of being or needing a lot of forward passes, but actually our hardware can deliver this fast inference. So this is again the setup from Besançon, and what we started when I arrived there, we started with simple tree search algorithms. So you have your setup, you project your images into the system, the laser processes the information non-linearly, and then you have the DMD here at the output, where you can flip mirrors back and forth, and based on if the error improves, you stay there, or either you go back. And we tried this for the MNIST classification. We see that, first of all, here in blue, for the Boolean weights, which you can encode with the DMD, you see that the error goes down. And what we further saw is if you go to a two-phase forward pass, where you have like first positive weights, and in the second path you have negative weights, and then you subtract the signals, you actually can improve the performance quite a lot. And this all is just based on this random search algorithm. And you see this converges within 500 epochs. So this is actually in real time, just around a minute. And based on this, you can already see that these search algorithms can work. However, so far, our output weights here are just binary and probably not optimal. We then scale towards more difficult problems with this trinary weights that are -1, 0, and 1. We use the two phases for that, and we do the 10-class classification. We record these images of the VCSEL surface. We apply the weights, and you see that with the epochs, you get an improvement in the error. However, the error does not go, the testing accuracy starts to stop around 83, which is because of the limited resolution. What we could show then is that if you increase the size of the VCSEL image on the DMD, you increase the size, you get more weights, and based on this, you also could improve the performance, but this was really like in small steps. So we used, in the beginning, 2 times magnification and then scaled up towards 4, and we just increased in a couple of %, but we didn't got beyond this 84% in the testing accuracy. So the idea was to replace this DMD with an SLM, where you have 10-bit resolution of the weights. However, then it becomes quite hard to just use these random search algorithms. And therefore, the goal was to use more advanced algorithms. And here the idea is quite simple. We wanted to sample out the gradient of the system without having actually knowledge about the model. What we do here is we use two forward passes. In the first, we have our WK, that's just our weights we set. And then in the second, we slightly perturb those weights. We get two errors, E and E delta. And then based on these error measures, we can compute an update of our weights towards a more optimal solution. And just to show you that we actually can approximate the real gradient of our system, we simulated here a neural network that's again in the digital domain. And we just used a couple of these forward passes and computed the gradient here and compared this approximated gradient with the real gradient of the system. And to compare this, we used the cosine alignment between the two vectors. And you see that the more you sample your system, the more alignment you get with the real gradient of the system. And then there are a couple of parameters like how strong is the perturbation. So this is with the hyperparameter tuning. But if you find the right way, you see that there's like a good agreement or increasing agreement between the sample gradient and the real gradient. However, this is not fully efficient. And we looked into literature, and there are actually some evolutionary strategies that exploit these kind of mechanisms. And what we found here are two algorithms that are called covariance matrix adaptation and parameter exploring policy gradient. And they both work on the same idea. Here, you don't start with an initial set of weights. You actually start with an initial distribution of weights. So you get for every weight, mean and the standard deviation. So you get these ellipsoids in the parameter space. And then you sample population within this ellipsoid. So here you can see that's the starting ellipsoid, that's the initial condition. And while updating your algorithm, you update the mean of this distribution and also the standard deviation. So you see the ellipsoid starts to elongate in certain directions. And based on this, you can get closer to the minima of the function, which is here a test function, and the minima is around here. I have also a video of this, where you can see how the two algorithms work. And what you see here is that the covariance matrix adaptation converges much faster to the minima because it computes the covariance between the parameters. And therefore, the update is much more precise. However, to compute this covariance matrix adaptation, you need the computation of the covariance matrix, and this scales quadratically in the number of parameters. So you have a bit overhead on digital computation that you need to do. On the other side, you have the parameter exploring policy gradient. There you see it needs much more epochs to find here something that is close to the global minima. However, the computation that you're doing digitally scales linearly with the parameters of the system you want to update. Looking at the videos, it looked like the CMA converged much faster. However, as I said, the scaling here is different, and therefore we wanted to compare not only like how many epochs it takes, we actually wanted to see how much time does it take. And there in the time, we also include like those computations that scale differently. And when we do that, we see that actually if you use a system with 1,000 parameters, that while in epochs, the PPG algorithm is much slower, if we look at the time axis here, we see that they almost start to overlap because we can do much more forward passes with the PPG because the computation of the next weights is just much faster. So here you already see that's kind of a different perspective, while this is more the digital one where you have time just mentioned as epoch. We here start to talk about the time in seconds, and then you see that actually the learning algorithms have different properties that you need to consider if you want to train a physical substrate. Now we applied these algorithms to train a neural network, which has 150 neurons, and in this case has 1,500 parameters only in the output weight. We train with 1,000 samples. That means we have 1,000 forward passes for different parameter settings through the setup. And then we can see that with the number of batches, that means the number of training data we pass through our system, we get an increase in the testing accuracy. And here in the different color scales, we compare different resolution of the weights. So as I said, the output weights in a physical substrate can have different resolutions. They are not floats anymore. They have restricted resolution. So here we looked at from 2-bit to 12-bit. And you see that 2-bit loses a lot of performance. However, if you go towards 6-bit, you already see that everything beyond 6-bit actually aligns on the same performance. And that means that to train this network, a resolution of 6-bit is sufficient. So you don't need this full float resolution anymore. And finally, in a physical system, you not only have restricted output, restricted resolution in the weights, you also have noise in the system. And here what I show is we train 150 neurons. Now we train the input and output weights at the same time. So the full setup is now trained. And we use different noise scales and 10-bit resolution, which is the same we have later in the setup. And what we can see is that the system that is untrained, that only trains the output weights, which is this brownish color here, we see that there's a strong degradation together with the amount of noise you put on the system. However, if you start to train, the system finds a way to make the entire setup more robust. And you see that actually all these setups where we train input and output weights align almost on the same performance. That means during the training with the PEPG algorithm, the system can really get more robust against noise and also increases the performance quite a lot. However, yeah, this needs to be said. These effects of the robustness against noise might change with the nonlinearity. What I used here as a nonlinearity is just the squared, but this might be different for 10H or whatever nonlinearity you have in your physical system. Finally, the question, did we succeed with those ideas to train the physical hardware? And for the large area VCSEL, what we right now could show is that we can train 10-bit resolution, output weights with 10-bit resolution in the setup. So we will put here an SLM. We can actually reduce the performance, increase the performance of the system. And right now, Anas is trying to also train the input weights. So this is in progress. However, we face a couple of challenges there, which I also want to talk about. Because if you train these different weights in the setup, you need to consider that those weights might have quite different impact on your system compared to those weights. That means you need to start to have different learning rates for input and output layer. You need to have like different time scales for updating the input and output weights. And these are all like new perspectives you need to take into account if you want to train physical substrates. On the other side, for the photonic integrated circuit, what we could achieve is a partial optimization towards simple filter functions. So we have target filter functions. We use the PEPG, we optimize towards them, but we never reached like low error rates. And here the challenge comes from the thermal crosstalk between the Mach-Zehnder modulators here and the time it takes for the system to converge. So we, in the end, had some problems with the consistency of the setup and also the stability of the chip. And again, here in digital computing, you would not think about these perspectives. But as soon as you move to a physical substrate, I think it might be even important to include like measures for consistency during the training, so that you, while training or optimizing your setup, you also know what is actually going on and if your system fulfills somehow the requirements you expect from it. With this, I want to conclude my talk. So I showed that for going towards new computing hardware and paradigms, there's on one side the task of designing new computers and substrates, and on the other side, you need to think about how can we program these physical computers. The programming and learning of these physical computers needs to fulfill new criteria that are not there for digital computing. And for the example of the photonic substrates, I showed that the evolutionary strategies might have some good arguments to use them. However, you need to think about the physical computer as well. You cannot just take the learning strategies and apply it. And finally, is the learning strategy all you need to use your physical computer? I think in what I learned from this year, let's say, is that it's important to exploit, or a good learning strategy is important to exploit the full potential of your physical computer. And there needs to be a shift from this small scale, coarse-grained parameter optimization like in reservoir computing to a more fine-grained, local, large-scale optimization of parameters. Then there needs to be much more work done to design efficient learning strategies. That means you need to, or we need to think about more sampling, to how to get more sampling efficiency and scalability in these learning strategies. We need to consider temporal dependencies. And I think in the end, it might make sense to see the optimization of these physical computers a bit more from a dynamical systems perspective. And the last point, this designing of physical computers and optimizing them is not a separate process. I think it makes sense to co-design the physical computer together with a learning strategy in mind, and that this might enhance the design as well as the learning in the end. With this, I'm finished, and I'm looking forward to your questions.
Thank you, Mirko. Do you have any questions? Yeah.
I did not realize, thank you very much for the talk, very, very interesting. I did not realize much where you put the noise when you compare when you train both output input and then only the output here. Where do you put the noise?
The noise here is actually within the nonlinearity. So there is an additive term. You have on one side the states of the system, and then an additional term for some random noise.
Okay.
And then the idea is that you push the states towards a part in the nonlinearity where you have some kind of compression. And there are different parts. For example, if you think about the tan-H nonlinearity, in the nonlinear part, you actually really can compress the noise, while in the linear part, you would just upscale it. And I think the learning algorithm finds a way to exploit the nonlinearity better. But this was something I would I would like to further look into.
Also, may I ask a second question? What is the advantage of putting this multimode fiber in the system? Because at the end, it's a linear mix of the inputs.
Yes. So the idea is, or what we started with, is not having this SLM in the input. It was just that the mixing of the input data and imaging on the VCSEL was mainly based on this random scattering within the multimode fiber. We now put the SLM here. And what we hope for is that when the information is encoded in the intensity, you have it all, let's say, locally at a certain spot. You apply locally some phase change. And then within the multimode fiber, you get something that is more like a matrix multiplication. While this part is kind of a Hadamard product, here you get towards more matrix-like multiplication, and you get different information on local sites here on the VCSEL surface. So the idea is just to get a better mixing of the information within the multimode fiber. Yes, no, there's nothing nonlinear. Yes, exactly.
Thanks. Ingo, I think you have a question.
Yes. First of all, thanks for the nice overview and also for the didactically nice presentation. I enjoyed it a lot. So what your presentation shows, and also Claudio's question, is that in the end, we need to know about the physical properties of the system we want to use to compute, right? And we would need to characterize that in detail in order to see which strategy could be exploited or adapted in the most efficient way. That's why I also wanted to add to Claudio's question. I fully agree with him. It's not entirely clear what the multimode fiber does in this concept. If you use a Hadamard product in the SLM, you mix it up completely again in the multimode fiber, right? And I would think that it would make more sense to try to see what parts of the VCSEL surface, for example, are dynamically responding and which parts are less responding, because you don't have a homogeneous profile in the emission. Is it possible to adapt? So that's in the end my question. Is it possible to adapt the optimization procedure to the physical properties of the reservoir that one can characterize? It's not a reservoir, sorry, but necessarily, but on the physical properties of the system or the physical computer.
Yeah, I think this is a really important point, and this is when I talked about, or let's say what we do here is unaware of any, let's say, properties of the VCSEL, because it's just a random brute force search algorithm. So you don't really have any information in the learning algorithm about your setup. However, if you move to these more advanced optimization schemes, you compute some properties and you encode them in the mean and the standard deviation for every weight. So what we hope for is that while optimizing the system, actually also the learning strategy gets a bit more adapted towards the physical properties of the VCSEL. That means that weights that are, or how to say this, weights that encode certain information, let's say on the border or the outer shape of the VCSEL, might be updated differently to weights that lead to information in the center of the VCSEL. So this is a bit the idea, or why we like these algorithms. During the optimization, actually your training algorithm also optimizes a bit towards the physical substrate you have.
Mm-hmm. Thank you.
Other questions?
You mentioned that you compare training only the output weight, but also the input weight and the output weight. Did you try to, or do you know what will happen if you train only the input weight?
We also tried this, and you definitely can get some kind of optimization. But let's say for this figure, you see that just training the output weights gives you already a lot of the performance here. And if you would just train the input weights, I don't have the numbers, so I can't show much, but I would expect that you need some structure in the output weights to extract the information. And if this structure is randomly, you don't get the same performance. And what we tried is, for example, to train the internal weights for this MNIST classification. And we saw that here, for especially for this image classification, the input weights have a stronger influence on the performance compared to the internal weights. But this is, I say, especially for images, that might be different if you want to do time series prediction, because then your internal weights encode somehow the memory and the temporal processing of your network. And then it might be that the internal weights are more important.
Thanks for the talk, Ian. I also have some questions. One is, how did you get to the 4 seconds on slide 4? Because you said it infers at 15 kilohertz, the system. Like,
yeah, it's relative to the number of images you have in the data set.
Okay.
So you have
Just the whole data set.
60,000 images for the training data set, and then we get
Okay.
to the 4 seconds. Yeah, sorry, that
And,
was not clear.
On slide 6, where you just were, which kind of network architecture did you use in your digital simulations? Or
So what we used is a recurrent neural network even for this image classification. Actually, it's not needed to have a recurrent network. However, if you think about a physical substrate, you always will have like some temporal dependencies. And we just wanted to have this also in the simulations. That's why we decided for a recurrent network. And yeah, so this is just a randomly connected recurrent network.
and how densely connected is it?
I think it's quite sparse.
Okay.
So I usually use networks that have like 2% of connectivity.
Okay.
But it doesn't matter so much. So we tried a lot to change also the parameters of this network, for example, the spectral radius. But as you always operate the system in the fixed point, it didn't have strong influence.
And could you go to slide 10, please?
Yes.
Because I had a question there, but I was.
10. Sorry.
Yeah, true. And this is a question towards, I could just look it up in the paper, but since you've probably read it, or definitely read it, I think, do you know which physical system they used there, or did they use several physical systems? And oh yeah.
In the left, they use different ones. So they have
Okay.
the optical, which is, I think, a crystal with some nonlinear effects, where they both, like the crystal is kind of unaltered, but they encode the parameters also in the input. So they send a signal, or let's say 2 signals, one with the parameters that modulate how the crystal reacts to the input that encodes like the image, for example. So it's kind of a pump probe thing. But they also showed that it works for like, I think it's acoustomechanic things, and they use some weird physical substrates, and they can optimize them with that.
Okay, thanks a lot. Yeah.
One short one, but could be more relevant to ask Hannes, because we have talked about this system that they have in Besançon. Have you validated the impact of the nonlinearity that it is actually here without a model as a black box that you have in the VXL, that it contributes to the output performance? Because eventually you have the nonlinearity at the photo detection. It is a system that has a relatively high error for computation. So what is the impact of including this VXL in the system?
So I think there are 2 things to consider here. First of all, people showed already that if you put a photodiode here, you can optimize and you can learn image classification. So just using the square nonlinearity of the detection might be enough. However, what you do then is you convert your optical signal into electronics, and you're kind of lost. If you want to build like more complex systems, the VXL will allow you to stay in the optical domain. And then you can, like in Besançon, they also now think about like deeper architectures. That means they couple VXLs into each other in a row. And then you can exploit the nonlinearity of the VXL to build these deeper systems. But it's true, like it's not fully necessary, but it gives you like, for the scale of the VXL, you get a lot of linearly independent states. And I think together with the optimization, this is quite a good idea to do.
I also have another question. Thanks, Mirko. So in slide 18, when you're comparing these methods of evolutionary strategies, in this plot on the right bottom, you are already adding time in seconds. So is this a numerical simulation? Do you consider anything from the hardware already? What did you have in mind?
So the idea is here that every forward pass takes the same amount of time for both setups. So this is excluded. The only time we measured here is the computation of the next distribution. So we have this kind of distributions, and for every epoch you get a new set or a new distribution, and the computation of this update of the distribution takes a certain amount of time. And this is here, it scales quadratically, and this just takes more time, and therefore you can do this a larger amount of updates within the same amount of time.
Thanks. Did you have a second question, Ingo, already? Or it
Yes, I
was-
had a second question.
Go ahead.
Coming to your point, you motivate in the beginning that training the input weights is certainly in order to improve the performance of the task. What about robustness? So do you gain, if you compare a system where you only train the output weights or a system where you train input and output weights? Because the methods you present certainly are a little bit sensitive or more sensitive for the input weights with respect to robustness, maybe. So that's why I asked.
I think I can only partially answer this, because what we did for the noise included optimization. I show that using the input weights actually can give you this nice robustness against the noise. And with this system I used here, I think there are also, like, the nice thing if you optimize the physical substrate directly without any digital model around, the optimization takes the robustness a bit into account. So you will see that if you have some just particular solutions, the algorithm will not go there because it samples on a huge distribution, and then it will see that certain regions might not be that stable. But in general, I don't feel so comfortable saying that this algorithm is fully robust against certain degradations of the substrate or whatsoever. So I can't fully answer this question.
Thanks a lot.
I think there are no more questions for you, Mirko, so thanks a lot for your presentation.
Thanks a lot, Mirko.